Hi everyone, welcome to Mathly. Today we are diving into Naive Bayes Classification, a fundamental algorithm in machine learning. It's based on the Bayes theorem and works well for text classification, spam filtering, sentiment analysis, and even medical diagnosis. While basic naive Bayes models have limitations, more advanced Bayesian methods like those used in modern language models offer significant improvements. We'll touch on these more when we go along this video. And the best part, I'll show you how to use orange data mining to apply naive Bayes classification step by step. Let's dive in. Imagine you're a doctor diagnosing a patient based on their symptoms. You have a list of possible diseases and their probabilities based on past cases. If the patient has fever, sore throat, and a headache, you can calculate which disease is most likely based on previous data. That is the basic idea behind naive Bayes classification. It predicts a category based on given features, assuming that all features are independent, which is why it's called naive. For example, in spam filtering, it assumes the word win appearing in an email is unrelated to the word price, even though they often appear together in actual spam messages. Even though this assumption isn't always true, naive Bayes still performs well in real-world applications. This algorithm is widely used in email spam detection, document classification, recommendation systems, and more. Now, let's see how it actually works. Naive Bayes is based on the Bayes theorem, which states that the probability of an event happening is influenced by prior knowledge of related conditions. The formula looks like this. The probability of A given B is equal to the probability of B given A times the probability of A divided by the probability of B. Let's break this down into simple terms. Probability of A given B. The probability of class A, for example spam or not spam, given some observed data B, for example words in an email. Probability of B given A. The probability of seeing the given data B if we already know the class is A. Probability of A. The prior probability of class A, or how often that class appears in the dataset. Probability of B. The probability of observing B regardless of the class. So how does this work in real-world classification? Let's take spam filtering as an example. Step 1. Training the model. The algorithm first learns from a dataset of labeled emails, some marked as spam, others as not spam. For example, in a dataset of 1000 emails, 200 emails are spam, 800 emails are not spam. Now let's analyze word occurrences. The word win appears 80 times in spam emails and 5 times in non-spam emails. The word offer appears 50 times in spam emails and 10 times in non-spam emails. Step 2. Calculating probabilities. When a new email arrives, the model looks at each word and checks how often it appeared in spam versus non-spam emails in the training data. Let's say our new email contains win a free offer. First of all, let's compute the overall probabilities of an email being spam or not spam in the dataset. Probability of spam is the number of spam emails divided by the number of total emails equals 200 divided by 1000 equals 0.2. The probability of not spam is the number of not spam emails divided by the number of total emails equals 800 divided by 1000 equals 0.8. Then let's calculate the conditional probabilities of the words win and offer appearing in spam versus non-spam emails. The probability of win appearing in spam is the probability of win given spam, that is 80 over 200 or 0.40. The probability of win appearing in non-spam is the probability of win given not spam, that is 5 over 800 or 0.00625. The probability of offer appearing in spam is the probability of offer given spam, that is 50 over 200 or 0.25. The probability of offer appearing in non-spam is the probability of offer given not spam, that is 10 over 800 or 0.0125. Since naive Bayes assumes independence between features or words, we calculate the joint probability. The probability of the words win and offer appearing given the email is spam is the probability of win appearing given the email is spam times the probability of offer appearing given the email is spam. This gives us 0.40 times 0.25 equals 0.10. The probability of the words win and offer appearing given the email is not spam is equal to the probability of the word win appearing given the email is not spam times the probability of the word offer appearing given the email is not spam. This gives us 0.00625 times 0.0125 equals 0.000078125. Step 3. Making a prediction. Suppose you receive a new email containing the words win and offer. Now let's classify it as spam or not spam using the Bayes theorem. To predict whether the email is spam or not, we will apply the Bayes rule. The probability of the email being spam given the occurrences of the words win and offer is equal to the probability of the words win and offer appearing given the email is spam times the prior probability of an email being spam divided by the overall probability of the words win and offer appearing in an email. The probability of the email being not spam given the occurrences of the words win and offer is equal to the probability of the words win and offer appearing given the email is not spam times the prior probability of an email being not spam divided by the overall probability of the words win and offer appearing in an email. Since the overall probability of the words win and offer appearing in an email is the same for both cases, we can compare only the numerators. The probability of the words win and offer appearing given the email is spam times the prior probability of an email being spam is 0.10 times 0.2 equals 0.02. The probability of the words win and offer appearing given the email is not spam times the prior probability of an email being not spam is 0.000078125 times 0.8 equals 0.0000625. Since 0.02 or spam is greater than 0.0000625 or not spam, the email is classified as spam. To put it simply, Naïve Bayes calculates the probabilities for each possible category and picks the most likely one. It's fast, efficient, and great for working with large datasets. Let's take a look at how we have set up our workflow in Orange Data Mining to perform Naïve Bayes classification on the diabetic patients dataset from Kaggle. First, I have imported the diabetic patients dataset from my local machine. This dataset contains medical data about patients, specifically their glucose levels and blood pressure. The goal is to classify whether a patient is diabetic or non-diabetic based on these two features referred to as glucose, blood sugar level of the patient, blood pressure, recorded blood pressure. After loading the dataset, I have used the data table widget to inspect the data. Here we can see the key attributes. The diabetes column as the target variable and the glucose and blood pressure columns as the feature columns. The dataset contains 995 instances. The next step is applying the Naïve Bayes classifier. Naïve Bayes is a probabilistic model that calculates the likelihood of each class, diabetic or non-diabetic, based on the given input features. It assumes that all features are independent, which simplifies the probability calculations. It is especially useful when working with categorical or numerical medical data like this. By connecting the trained data to the Naïve Bayes widget, we are training the model to recognize patterns in diabetic patients based on their health metrics. Once our model is trained, it is crucial to evaluate its performance to determine how well it generalizes. The Test and Score widget in Orange Data Mining helps us assess the quality of our Naïve Bayes classifier for diabetes prediction. The model is tested using 5-fold cross-validation, meaning the dataset is split into 5 parts and the model is trained and tested multiple times to get a more reliable accuracy estimate. Stratified sampling is enabled, ensuring that both diabetic and non-diabetic cases are evenly distributed in each split. Let's take a look at the performance metrics. AUC is 0.969. This shows how well the model can separate diabetic and non-diabetic patients. A value closer to 1 means excellent performance. Accuracy is 0.915. Classification accuracy represents the percentage of correctly classified instances. Here, the model achieves 91.5% accuracy, which is quite promising. F1 score is 0.915. This balances precision and recall, meaning the model is good at both detecting diabetic patients and avoiding false alarms. Precision is 0.915. When the model predicts a patient has diabetes, it is correct 91.5% of the time. Recall is 0.915. Out of all actual diabetic cases, the model correctly identifies 91.5% of them. MCC is 0.829. This is a more advanced way to measure how well the model performs overall. A value closer to 1 means the model is making very accurate predictions. In simple terms, the model is doing a great job at predicting diabetes, but further tuning or testing with other models could improve performance even more. To better understand how our model performs, we use the confusion matrix, which breaks down predictions into 4 categories. True positives. The model correctly identified 457 diabetic patients. True negatives. The model correctly classified 453 non-diabetic patients. False positives. 44 non-diabetic patients were mistakenly classified as diabetic. False negatives. 41 diabetic patients were misclassified as non-diabetic. What this means for our model. The model does well overall, correctly classifying 910 out of 995 cases. The number of false negatives, 41, is important in medical applications since missing a diabetic case could have serious consequences. The 44 false positives mean some non-diabetic patients are wrongly classified, which could lead to unnecessary medical tests. By analyzing this matrix, we can decide if we need to fine-tune the model further to reduce errors, especially false negatives, to make it more reliable for real-world diagnosis. To assess how well our model generalizes to new cases, we use the test data and predictions widget. This test data contains 10 rows of patient records that the model has never seen before. By testing on this unseen data, we get a better idea of how well the model performs in real-world scenarios rather than just on training data. The predictions widget shows the classifier's results for each test case. It includes predicted class, diabetic or non-diabetic, probability score for each class indicating how confident the model is about its prediction. Left-hand value is for 0 and right-hand value is for 1. Actual class, the true diagnosis from the dataset. Error column, highlighting the model's misclassified portion of a particular result. Looking at the 10 test cases, the model performed well with only one misclassification. In the 4th row, the actual class was 0, non-diabetic, but the model predicted 1, diabetic. The error probability for this incorrect classification was 0.643, meaning the model was somewhat uncertain in its prediction. This analysis helps us understand if the model is making strong, confident predictions or if there are cases where it struggles. Since the model only made one mistake out of 10, it suggests good performance, but we could further refine it to reduce errors, especially in critical medical applications where misclassification can have serious consequences. And that is our complete workflow for training and evaluating a Naïve Bayes classifier in Orange data mining. We successfully loaded the data, trained the model, tested its accuracy, and visualized the predictions. And now, we will look at some real-world usage scenarios of this model. Naïve Bayes classification is widely used in real-world applications where making quick and reliable predictions is essential. Let's explore some practical use cases where this simple yet powerful algorithm plays a crucial role. Sentiment analysis in social media and reviews. Businesses use Naïve Bayes to analyze customer reviews, tweets, and feedback to determine if people have positive, negative, or neutral opinion about a product or service. By processing words like amazing, terrible, or okay, companies can measure public sentiment and make data-driven decisions. Medical diagnosis and disease prediction. In healthcare, Naïve Bayes helps doctors predict diseases based on symptoms. For example, if a patient has fever, sore throat, and fatigue, the algorithm calculates the probability of different illnesses like flu or COVID-19 and suggests the most likely diagnosis. This aids in faster and more accurate medical decision making. Fraud detection in banking. Banks use Naïve Bayes to detect credit card fraud by analyzing past transactions. If a sudden, high-valued purchase occurs in a different country, the algorithm checks the likelihood of fraud based on past spending patterns and can trigger security alerts or block transactions. Text categorization in news and document classification. News organizations and search engines use Naïve Bayes to classify articles into different categories automatically. For instance, an article containing words like election, government, and policy is likely categorized under politics, while another article with stocks, market, and finance falls under business. This helps users find relevant content quickly. Advanced Bayesian methods in AI. While Naïve Bayes is simple and effective for many tasks, modern AI applications like large language models such as ChatGPT or Gemini extend Bayesian principles with deep learning techniques. These models go beyond basic probability calculations by incorporating massive datasets and complex neural networks, allowing for more nuanced and accurate predictions. From analyzing customer opinions to diagnosing diseases, detecting fraud, and categorizing text, Naïve Bayes Classification is a versatile tool in machine learning that makes automated decision making faster and more efficient. And that is how you can use orange data mining to apply Naïve Bayes Classification in real-world scenarios. We explored how the algorithm predicts categories based on probabilities, how it assumes feature independence, and how it is used in different fields. If you found this video helpful, don't forget to like, share, and subscribe to Mathemly for more data science tutorials. Comment below with what you would like to learn next. Thank you for watching and see you next time.